Yes, yes.
Yeah, yeah, okay. So yeah, so welcome to the KT session on clustering. So first of all, we'll start with what is clustering. So it is basically the task of grouping together some data points on the basis of some similarity. So it's like an unsupervised form of learning in which there are no truth labels. It's like the model learns from itself and like clusters the data, which is like groups them together into different categories based on some similarities which they have. So due to this, we can find some hidden patterns in the data, and it can also be used for like things such as pre-processing, feature engineering, etc. So as you can see in this picture, like we can clearly see that there are three clusters, and the main motive of us is to like convert it into a form such that these three are separable in some sort of clusters. So these are some few types of clustering that we'll be covering today, which is like k-means clustering, hierarchical clustering, CURE, which is clustering using representatives, density-based clustering, Gaussian mixture models, and expectation maximization algorithm. So first of all, let's start with partitional clustering. So it's basically the normal traditional form of clustering. Like we divide the data set into non-overlapping clusters, and each point is only like belong to only one cluster. And the goal is to maximize, like optimize a certain criteria like the intercluster similarity or distance. So like you group data on the basis of distance. So this is like all of us are like clear to all of these things. The important part in partitional clustering is that we need to specify the number of clusters that we need to form. Like the model, like we need to pre-feed it before itself, like how many clusters we have to form. And another important thing is that there is no hierarchy or tree structure in this. So yeah, so like a part of partitional clustering is k-means clustering. So in this, yeah, we start off with data points like say x1, x2 till xn. They're like n data points, and the goal of the algorithm is to find k centroids and like k clusters, which group them into k different clusters, and they have k centroids u1, u2 till u1, and the clusters are c1, c2 till cn, such that within one cluster the sum of squared distances is minimized. Like every point belongs to a particular cluster in such a way that the center of that particular cluster is closest to it. So this is the basic structure of what k-means clustering is. And apart from that, we have two different things as well, which is k-medioids and k-medians. In k-medioids, we use everything is similar except for the fact that in this we use the actual data points as centers. So suppose in this, like in k-means clustering, the center could be any random point, like suppose say here or here. In that, it need not necessarily be a data point from the given data set. But in k-medioids, the actual center which we choose as a centroid is an actual data point. And for k-medians, it just uses the concept of medians instead of means. So instead of taking the average distance or some sort of thing like mean, we take the median of the distances, and that particular point is taken as the centroid or like the median for that particular thing. So this is more or less about the k-means clustering, like how it looks. So like this is how we do k-means clustering. Like this is like you can look at the picture. So like these are three different clusters, and the goal of the algorithm is to find like group them together in three different clusters, and these should be the centroids of it. So let's move on to the steps of the algorithm. So first of all of the we choose k different centroids randomly. Like the algorithm first of all chooses any, like in this case, k is three. So we take three different, like randomly three different centroids are chosen, and then each data point is assigned to the nearest centroid based on the Euclidean distance. Like suppose if I take some data point center here and here and here, like these are the random initialized centroids, and then every data point, like the distance from each of the centroids is calculated, and from which the distance is minimum, that like that particular data point is assigned to that particular cluster. So this is how it works. So first of all, you take random chosen centroids, you assign a particular data point to a particular cluster whose centroid is like at the minimum distance. And then after that, a few of the points will get assigned to that particular cluster. Say if I had a center here, some of the points from this would be assigned to this. And if I had a center here, other points would be assigned to this cluster. So based on whatever points I have assigned to say the yellow cluster, using that data points, I'll again calculate the centroid for that particular cluster. So like again and again, we'll get something like which will repeat itself. So it's like you calculate a centroid and then you use the data points to calculate the centroid again. And based on that, you move in a particular direction until it converges. So I hope I'm clear with this. And in a mathematical form, you can write it as an objective function where you have to minimize this j. In this case, this is the distance between the centroid and the data point, and you minimize it for each cluster. And this is for like each point in the particular cluster, and this is for like I equal to wait. Yeah, this is for each centroid. Say each cluster, we have I equal to 1, 2, 3. So we take three different clusters and we minimize it for every of them. So this is the steps of the algorithm which we use in k-means clustering. So do I have any doubts still here? So yeah, I'll take it as no doubts then. Yeah. Am I audible?
Yes, you are audible.
Yeah, okay. So now the important part is how do we find the optimal value of k? So like in a particular data set, we need not necessarily like in this particular case, it was very evident that we can easily find three clusters. But suppose we have a very large data set. So how do we find that what is the necessarily like optimal value of k? So basically, we have a few methods for this. One of them is the elbow method, the other is Szilard score, and the Davis-Boolean index. So basically, what do we do in this is like we take particular values of k, say k equal to 1, k equal to 2, k equal to 3, and based on the k values, we calculate what is the quality of the cluster. And obviously, it's very evident that for which the quality of the cluster would be the best, we'll take that k as the optimal value of k. So the first is the elbow method. So before moving on to this, we should understand what is WCSS. So WCSS is nothing but it stands for like within cluster sum of squares. So it's like you compute the sum of square distances for each point within a particular cluster. So suppose you have a cluster which is like say yellow cluster and you calculate the sum of square distances from every point to the cluster center and you compute all of them. So that would be the WCSS term for that particular cluster, and you add all of that for all clusters, which would like give you the sum of SSE, which is like sum of squared errors, sum of square distances. So now what do we do is like we plot the graph between WCSS and the K on x-axis, and this is on the y-axis. So basically we get a graph like this, which is quite evident because suppose you have, I'll go to the thing. Yeah, this is the center of the particular cluster. Suppose this was the center, then you would get like the distances, the sum of square distances would be very large. So in that particular case, the distances would be very large. And suppose if I like instead of three centroids, I'll take like five centroids or six centroids. In that particular case, the value of the thing would necessarily like the WCSS would decrease because for these, some of them I would have a different center and other of them I would have a different center. So in that case, the value towards the center would decrease more or like it would decrease. And if I take only one center for all of them, then all of them would be in one cluster. But in that case, if I calculate the distance, like sum of square distance for every point, that would be very large, right? Because all of the distances, if I calculate from the center for all points, it would add up and become a very large value. So if we plot a graph for very less value of k, say only one cluster, the WCSS score would be very high. And if we take a huge amount of clusters till say k equal to like 1,000, suppose if we have 1,000 data points, and if we take each of the data point is a cluster, in that case, the WCSS would tend to zero because every point is at the center of its cluster. So the graph would be like it would decrease as the value of k increases. So in that particular case, what do we have to find is like we have to find an optimal value of k beyond which the decrease is very less. Like there's not much improvement. Like as you can see in this k, like at k equal to k1, the value of WCSS decreases very much, but after this, the decrease is very not very rapid. It's like there's not much improvement. So like this looks like an elbow, and therefore it's called as an elbow point. So this is usually taken as the optimal value for K. So this is how the WCSS method or the elbow method works. So in that case, like this is more or less about it. And the other one is the Szilard score. So in that, so this is basically a metric which evaluates the quality of clusters measuring two different metrics or like two different things, which is like cohesion and separation. So like in cohesion, you calculate like it measures like how close the points are to the other points within the same cluster. Like takes into account like how close the points are to the other points in the same clusters, and it also takes account that how far the point is from other points, like from the points in the other cluster. So like it considers both of them. So the formula, the mathematical formula for this is SI for like a particular point I is BI minus AI by maximum of AI and BI. So AI is nothing but the average distance from point I to all the points in the same cluster. And BI is the average distance of point I to all the points in the nearest different cluster. So suppose if you have a cluster A and cluster B, for a point in cluster A, the average distance to all the points in the cluster A would be taken as the value of A in this formula, and the average distance of a point I to all the points in the other cluster B, that would be taken as the value of B. So in this case, we calculate SI is BI minus AI by maximum of AI BI. This is nothing but the Silhouette score. So suppose if in this case, yeah, the value which are like near one, like plus one, indicate that the clusters are very well defined. The values near zero indicates that the data points are very close to the boundary conditions, like it's on the boundary of two different clusters, and it cannot be necessarily classified where it is, or it's like very close to the other one, possibly like outliers or something. But or like in near one, it clearly indicates that the point is wrongly clustered. So this is the Silhouette score. And yeah, does anybody have doubts with this or the elbow method till now? Yeah, so I'll take it as a no and then I'll go forward. So the other one is Davis-Bolden index, which is DBI score. So the Davis-Bolden index evaluates the clustering quality on based on intra-cluster similarity and the inter-cluster separation. So when you're clustering data, you would want the clusters to be different, like separated from one another, and the points within the cluster to be like very close to each other, such that they're very compact and they're like well separated. As you can see in the thing, we can see that the clusters are like very well separated and all the points are like very close to each other and they're in a compact way. So this is like an ideal way in which we want the clusters to be formed. So for that, the Davis-Bolden index measures both of them, the intra cluster similarity and the inter-cluster separation. So the mathematical formula for this is 1 by k and then summation of I equal to 1 to k, the maximum of Si plus Sj plus Di and Dj. So what is Si? SI is nothing but the average distance of a point in cluster I to its centroid. Like if you have all the points in a particular centroid, you compute the average of the distance of any point in cluster A to its centroid. That is like SI, and Dij is nothing but the distance between the centroids of two clusters. So in this case, suppose if I have a very high value of SI or Sj, say, in that particular case, the average distance would be to the centroid would be very, very large, which is something which you don't want, because if you go to an ideal case, you want the distance, the average distance to be the center to be very less, because you want the points to be nearly like compact to it and like near well arranged towards the center. So that's why if you increase the value of SI, not, it's like the point get away from the centroid, which is not something good. And if you see Dij, it's a term. If you decrease this term, the two clusters will come closer because the distance would be centroids would be very less. So in this case, you can clearly see that we want the clusters to be separated well enough. So you want a value of Dij to be high and you want a value of Sij to be less. So in that case, we would always prefer a value of dBi to be very less, because Si should be less and Dij should be high. So the lower the dBi, it's the better. And at the lower the dBi, it means that the clusters are compact, like within themselves, the all the data points are well clustered and they are in a compact way, and the all the clusters are well separated, and it's like easier to classify all the clusters. So yeah, now we can move to k-means plus plus. So basically, what is a problem? There's a problem in k-means because in the starting there's a random initialization of centroids. So suppose like in the starting, all the data points, like all the centroids, are assigned randomly, which can cause a slow convergence, or like it can lead to poor clustering as well, or it may increase the computation time. In such cases, we tried the k-mean plus plus starts like it solves this problem, and it starts off with like well separate well spread initial centroids, and it reduces the bad clustering. So basically what you want to do is like you don't want poor clustering, and you want to like have a certain initialization which like boosts the computation time, or like it sort of leads to a better convergence. So in this case what you do is like first of all, you chose the first centroid randomly from the data. Like in k-means, all of them are chosen randomly, but in k-means plus plus, you just choose the first one randomly. And now for every x which belongs to the capital X, which is nothing but the set of points, you compute the distance to the nearest centroid. So like every point, suppose there are like three clusters, and every point you calculate the distance to the nearest centroid. And like you check like what is the nearest centroid, and you calculate the d of x, which is nothing but the minimum distance. So for the first one, we have only one centroid, and you calculate the distance to the nearest centroid. In this case, it would be the first centroid itself. And now you choose the next centroid randomly from the data points with the probability proportional to dx whole square, like in the denominator. Yeah, sorry, proportional to dx. So what you want is like the sum of this would be like sum of all the dx squares would be in the denominator and dx square would be in the numerator. So what you want is like this gives a higher probability to the data points which are like away from the chosen centroids. So what you want is like you choose the nearest, like you choose a point and you choose the other centroid which are like away from the current centroids. So this leads to a better initialization because suppose in k-means plus plus, like in the actual k-means, if all the three centroids are very close to each other, say 1, 2, and 3, we get very close to that would be a bad initialization. But in k-means plus plus, we choose the first one randomly, and other ones are the data points which are like taken in such a way that they are away from the particular centroid right now. So in this particular case, the centroids are already not very close to each other and they are very spread off, which is something we actually wanted to see in like separation part. We want like in the silhouette score, we also want the clusters to be very well separated. So in this case also like k means plus plus solve this problem and it leads to a better initialization by giving the higher probability to the points which are away from the given centroids. So this is k means plus plus, and now we can move on to the code implementation for k means. Yeah, just a second. Yeah, is my screen visible?
Yeah.
I think yeah. Yeah, cool. So for k-means clustering, we use sklearn. So this is like the code of how we implement k-means clustering. So first of all, we start off with importing the necessary libraries. Like from sklearn, we use k-means and we import it for the thing. And this is nothing but the importing libraries. Now we use a dataset, which is like the income CSV. So in this dataset, it's like a pretty normal dataset. You have the names of the people, you have their ages, and you have their income. So in this case, first of all, what is really important in K means like you need to scale the data. You need to bring like suppose this is 70,000, which is like a higher value, and 27 is very less to it. And in K means you compute the distance as Euclidean distance. So suppose if I had different features, this would be in a different range and this would be in a different range of values. So in this case, like if you calculate the distances, it wouldn't like it would be really bad because this would have a higher weightage over like higher priority or higher weightage in the formula or like the distance computation. So we want to do is like we scale both of them to a particular way in such the way like they are both between 0 to 1 such that more or less they contribute equally to the mathematical formula. So scaling is really important in k-means because we use the formula directly and different features have different ranges of values. So now first of all we scale the data using minmax scaler from the library, and then this is nothing but now we like yeah. And now, oh yeah, now we plot income versus age on like the graph. And as you can see, for different age groups, we plot what is their income. So these are nothing but the scaled quantities. So the age between zero point 0.0 to zero point 0.4 in the scale dimension, you have the income spread like this. For other dimensions, you have this. So like looking at the graph, it's easy to decide that you have like you're gonna have only three clusters, but we can use the Elmo method to find what should be the optimal value of K as we discussed in the presentation. So first of all, I like make a sum of squared errors. Like this is like the implementation. You just make a empty thing, and now you just for the range k 1 to 10, you calculate the different values of k, and for that you add the value sum of squared errors or like the sum of squared into all of these values, and now you just plot the graph. And as you can see here also, we get the like the optimal value at 3 because more or less as we move forward towards like away from 3, the improvement is very less, and here like there's a sudden improvement and you like get an optimal value at 3. So here we use the clusters as 3, and now we can like just fit the model and then use the predicted values. So for different values of you get like one, like for some values you get one, for some values you get the label as two, for some you get zero. So more or less the this thing assigns the thing like the label to the values, and now you like just fit the model, and now these are the clustering labels. And now just add this value, like we just add this value to the predictor, like the original data set to see like, yeah, this is Rob and this is the age income and he belongs to cluster one, or there's the other person who belongs to cluster zero. So now you can just, and one more thing is like we use this formula to like find the value, like the coordinates of the centroid. So you can find the centroid using this. And now this is nothing but the plotting of graphs, or like you make three different data sets out of this. You use the scatter plot, and then you use different colors, green, red, and black for like three different points. And now you just find you like just mark the centroids with the purple color. So you can see that using this, we can actually like using k-means, we found out the different centroids and the different clusters for the given data set. And we also used the like the elbow method to find what was the optimal value of k. So this was the part of implementation of k-means clustering. So if you have any doubts, you can ask, or we can move forward with hierarchical clustering right now. Does anyone have doubts, or can I move forward with this? So again, I think I'll take it as a no and then move forward with this. So the second part is hierarchical clustering. In this, so this is a bit different from the first thing, which was partitional clustering. In this, we have something known as a dendrogram, which is like building a tree using like clusters. Like this has a thing known as a dendrogram, which is like a hierarchical clustering. You can like we can figure it out from the name itself that this assigns some sort of hierarchy. So this is like a dendrogram, which we'll come to later. Like what is it? So this is like it builds a tree of clusters called the dendrogram, which is like a very important part of hierarchical clustering. And the second most important part is like we don't need to specify the value of k as we did in partitional clustering. Like we can just cut off the tree at a particular level to get the number of clusters. So like now things might get confusing, but like I'll just define this and then move forward to the next slide. So first of all, dendrogram is like a tree where it starts with all points as clusters, like all points are clusters of their own, and then it moves forward to like at the top, all of them are assigned to a single cluster. So like once you look at this graph, so suppose PQS and all of these points are like data points. And like at the starting, all of these points are taken as their own clusters. Like this is one cluster, this is one cluster, and all are like separate clusters of their own. Now, at one state, suppose P and Q are like combined to form one cluster, T and U are combined to form one cluster, and then S is also added to that particular cluster. And then at another step, R is added to one cluster. And then at the end, whole of this is nothing but one cluster. So you plot this dendrogram for different thresholds or values, and like it moves for like it moves from all of the points being in one cluster from up to like till down. All of these values are like different clusters of their own. So in hierarchical clustering, like we can also see that we can also like start with each like logically if we speak like we have like 100 data points, how can we like divide them into different clusters? We can start off with all the 100 points being in like a particular cluster, and then we can go on dividing the clusters into like two clusters and three, four, five, and then like make like go on till all of the 100 points are in different clusters of their own. So this is either we can proceed that way, or another way we can like start off all the 100 points as their own different clusters, and like go on joining each of the clusters, and then like combine all of them to find like make a single cluster. So these are like two approaches what we have in this clustering method. First of it is like agglomerative clustering, which is nothing but like starting off with each data point and then like merge all of them step by step until you have only one cluster left. And for divisive, it's like you start with one cluster and you go until you have like all data points as the separate clusters. So one of them is like just moving up the dendrogram, and one is like moving down the dendrogram. So I hope I'm clear with this. And Yeah, so let's move on to dendrogram. As I explained, it's nothing but like a graph or like a tree where you can see all of the data points being grouped together at different stages. And you can either move up or you can move down in hierarchical clustering. And the branches of the dendrogram are called clades. And each clade has one or more leaves. So at the end, you have like one, two, three, four, five, six, and seven, like six leaves of like the dendrogram. So this is like a mathematical approach, to, like what is dendrogram. So now let's move on to the linkage criteria. So suppose like you are combining two clusters, like we all deal with combining clusters or separating clusters in this method. So how do you combine different clusters? Like what is the criteria defining the distance between two? Like what is the distance? So either you could say that between cluster A and B, I can take the distance between the nearest points as the distance between the clusters. So this is nothing but single linkage. You use the distance between the two nearest data points in this in the clusters as the distance between the two clusters A and B. So the formula is nothing but pretty easy. Like you can just minimize the distance between each of the data point and you can find the minimum value. So this is nothing but single linkage. Or the other one is like complete linkage. You can find the distance between the 2 points which are like the farthest away, and then you can take that distance to be the distance between the like two clusters A and B. So this is also like simple only, like you can just find the maximum, like you can compute distances for all pairs and you can find the one which is the maximum of all of the distances. The other one is like a better for like usually what happens in maximum or minimum distance, like suppose there was a thing which was an outlier, like suppose all of the clusters were here and there was one point here, and because of that particular point, it was nearest like sorry it was near to some other cluster. So because of one outlier, it can be like two clusters can be merged together, which is like something which we don't want. And in the case of like complete linkage, we can also see that if a cluster, like if a point is very far away, because of that, it is like added and merged up to another cluster. So like it is very sensitive to outliers and it does not work well. But in the case of average linkage, what we can see is like you compute the data, like the distance between any 2 points, like any two of the pairs, and then you just take an average of all of them. So, and using that average distance, you like compute, like you just merge two different clusters together. Apart from this, we have the centroid linkage, which is like you compute the distance between two clusters or the distance between the two centroids. And you can have the radius and diameter linkage, which is nothing but you merge, like say, suppose you have one cluster and two clusters, you just merge both of them and you find a centroid of that. And like you find a diameter, like from one end to the other end. And that diameter can be used as like the distance metrics or like the distance criteria for linkage. So like this is how you define the linkages or like the distance between two clusters. So now the other thing is where to cut the graph. Like suppose you are like merging all the clusters like from being all single data points to like a whole cluster, how to decide like where you have to cut the graph to get a certain number of clusters. So as I explained before, like we can use the Szilard score here as well to find what is the optimal value of k, and we can like cut the cluster there itself to get the necessarily like the necessary amount of clusters which we have. So let's move on to the code implementation for this. So like, yeah, this is the hierarchical clustering code implementation. So we like import the necessary libraries like matplotlib, pandas, and numpy, and then we move forward. This is like a data set called customer CSV. In this data set, we have the customer IDs, the gender of the customer, their ages, the annual income, and their spending score out of 1 to 100. So what we need to find is like we plot a graph between spending score and annual income of a particular customer, and we'll try to cluster it using hierarchical clustering. So first of all, like you make the graph and then you just do the necessary points. You take out of the like using this function, you take these values and like get an array of that. And now we'll move forward. Like, yeah. So now you just use this SciPy cluster, like you import this library from this. You get this SHE or dendrogram function from which you can find the cluster. Like you can plot the dendrogram for all of the points. And like and I use the method of complete linkage here. You can also change it to like like the merge the clusters based on different linkages types. So like plotting the dendrogram is like using this library and then you can easily plot between the data. Now the other point is like how do you find the optimal value of k? So as I said, I use Szilard score for that. You just define a score thing which is like a list, and then for every k belongs to the range, you calculate the Szilard score using the using the function which we used here, and then like you calculate all of them and you plot the graph between the Szilard score and the value of k. So as you can see, as like for k equals to 2, like 2 clusters, 3 clusters, 4, 5, 6, and so on, we get different Szilard scores. So for 5, we can see that we get the maximum Szilard score, and the maximum the Szilard score, the better it is. So like plotting the graph and like calculating the value of Szilard score for all of them, we plot a graph, and from the graph, we get to know that the optimal value of k is 5. So now we just import the agglomerative clustering thing, and we put the value of n clusters equal to 5. We can also change it, but as we got the value of k optimal as 5, we'll put 5 for like the clustering part. And now I use complete linkage here. You can also use like other type of linkages to see how it works in that particular case. And now using that, you just predict the different arrays, like it assigns this to different labels, like 0 for one for some other cluster, 2, 3, 4, and like so on for different clusters. And now you just plot a graph between all of them, like how, like between the different datas, and like just, yeah, plotting the graph, you get different linkages. Like you get this is as one cluster, other 2, 3, 4. But suppose like we can also like change this and see how does it work with like single linkage. So in that particular, the labels would change. And in that case, you can actually see that this is not very well. Like you can see all of the clusters are classified as blue. So this is because, as I said in the PPT, that because of the outliers, the single linkage is very like sensitive to it. So suppose you can see that these were in the same cluster within the average, like the complete linkage. But as you can see, these points were very close. So are these points, and these points are very close. These points are very close. So because of that, if you take the minimum distance between the two clusters, like between the two data points in different clusters as the distance between the clusters, this tends to give a wrong thing in like in some sort of data spread or like data set like this, because of the fact that two, like there are very points which is like very similar. So in that case, you could actually go with like complete linkage. In that case, we consider like the maximum distance. So because of that, you get a different graph in this. So as you can see, using that particular linkage, we get a different clustering, and this is more or less very well. And also we can use average clustering for this. This is, yeah, using average clustering also, like you can see that it's somewhat better, but as you can see in this particular case, if you take the average distance, some of them are very close, some of them are very far. It more or less like cancels out both of them, and you get like this to be a singing cluster. So like choosing the correct linkage type plays a very important role in hierarchical clustering. And as you can see in this, we get different clusters based on which linkage type use. So this is like more or less the implementation, and the complete linkage gives a very good answer, like very good clustering for this, because it takes the farthest distance. So this is about the implementation of hierarchical clustering. So does anyone have doubts? I'll take it as a no again, and then so let's move on to one more method, which is like the threshold graphs. So here, instead of using data points directly, we use something known as a similarity matrix. Wait, hello, am I audible?
Yeah,
Yeah. So yeah, moving on to threshold graphs. So instead of using data points directly, we use similarity matrix. So yeah, so what is a similarity matrix? So in simple terms, it is like an inverse of the distance matrix formed between the points. So suppose you have like 5 points, say suppose 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. You find how similar those points are to each other in terms of like distance. So say suppose if you like use the distance matrix between them, you would come like you'll find the distance between all of them. Suppose between 1 and 1, the distance would be 0. Between 1 and 2, the distance would be like say 0.2, and between 1 and 2 again, that would be like the transpose of like the other elements would be same. So instead of like just take the inverse of the distance matrix, so you'll get a similarity matrix. So a distance matrix, it nothing but it describes the distance between any 2 points, like any two pair of points. And the similarity matrix is nothing but inverse, which says how similar are two points. Like if 2 points are similar, the distance between them is less, they're closer to one another. So this is how you form a similarity matrix between, like, say, 5 points and 5 points, and this is like the matrix between them. So yeah, before stepping into the threshold graphs, what we need to understand is like some a few points. Is like this is something like a matrix, but we need to proceed forward using a graph. So let me explain you what is this. So as you can see, like these are like some values. So instead of taking it as a matrix, we can think of it as some nodes and the values like 0.8, 0.3 as the weights between the nodes. So suppose like we just make some five random points, say 1, 2, 3, 4, 5 were the points, and between 1 and 2, the similarity matrix tells that the similarity is 0.8. So you take this, I'm sorry, you take this as a weight between them to be 0.8. And so between 1 and 3, you take it as 0.3. Like 1 and 3, it's 0.3. So you take the weight between this as 0.3. So in this case, you can proceed with a graph and you just look at it as nodes and weights between them. So you start off with this, and then yeah. And then make a graph, some sort of thing with like the weights point, like graph, like written on this, and you just make a graph like this. And now like to go forward with clustering, we need to solve something known as a min cut problem. So suppose I have this graph, and like if I remove this 1 to 2 edge, and like 1 to 2 edge, 1 to 3 edge, 1 to 4 edge, like all of these, like 1 to 2, 2 to 5, say, like this one, and this one. Basically, you try to cut all of them, then you'll get one cluster as 1, 5, and 4, and one cluster as 2 and 3, right? So what do we do is like, suppose we cut a few edges in this, we'll end up getting different clusters. Like all of them are like connected together, but suppose we like remove some connections. In that case, you'll get different components, like two different parts of like data. So this like, so what happens is like you need to understand that this graph plays a very important role because based on how you cut the graph, you're getting your clusters. So suppose if I cut a few components or few edges from this graph, you get what is called as a cut set. And what is a min cut? A min cut is nothing but you cut the edges in such a way that the edges which are cut off, like the set which is left has the least weight. Like you just cut it in such a way that the set has the least weight. It can have more edges, but you need to focus on how you cut it such that it has the least weight. So I hope I'm clear with this. If anyone has doubt with this, can ask right now. Yeah, so moving forward with this, yeah. So this is like a graph, and now like there's something called as minimum spanning tree and maximum spanning tree. So like you can just see that this is the graph, and like a maximum spanning tree is like which is nothing but a tree, like obviously, and it spans is like it connects all the vertices together, which has the least weight. Like suppose this was the graph, and I have to find a maximum spanning tree. So I would try to connect all the points in such a way that the weights which are used in these edges are maximum. So suppose I had 0.2, all of these values in it. I have to connect all the points. So obviously I'll take 0.8 and 0.7 for a maximum spanning tree, and you connect both of them. So like now you have 1, 5, and 2 connected, and now you have to connect 3 and 4 into this thing because a tree connects all of the points. So connecting 3 and 4. So you can either connect like 2 and 3 using 0.2, or you can connect 2 and 4 using 0.5, and 4 and 3 0.5. So what do we do is like for the maximum spanning tree, we want the maximum weight. So we have already taken 0.8 and 0.7, which is like the maximum. And now you connect 0.5 and 0.5. So in this case, you could, if you connected with 0.2, that would not lead to the maximum spanning tree because it wouldn't have the maximum weight. So you take 0.7, 0.8, 0.5, and 0.5. And now this is like a maximum spanning tree for this particular graph. So in a similar way, the minimum spanning tree is like it has the least weight. Like suppose you took 0.2, 0.2, 0.3, 4, 6 in such a way that all points were connected and it had the minimum weight. That would be a minimum spanning tree for this graph, and a maximum spanning tree would be like the one in which all points are connected such that it has the maximum weight. So yeah, so this is the minimum spanning tree and maximum spanning tree. So what you can do, like what we have to proceed in such a way that we can go with two things. Like if we are given the similarity matrix, we can use a maximum spanning tree and remove the edge with the least weight. So suppose this is a maximum spanning tree, and I made this like spanning tree for this particular graph. And now I have all these points connected. And now say suppose I have to divide this 5 points which are in like one cluster. Think of it to be in a one cluster, and you have to divide it into two clusters. So I can either cut 0.8 or 0.7 or 0.5 or 0.5. What should I cut? So technically, what I want is like in a cluster, you want all of the closer, like as I said before itself in the presentation, that you want a cluster to be compact. So you want the distances between the centroid or the points between in the same cluster to be very less. So suppose 1 and 2 points are together. Their similarities is like 0.8, which is like the distance between them is less. The distance between 1 and 5 is also less, 1 and 2 is less. But you can see 2 and 4 ka similarity is like less compared to this, which means that it has a more distance. So you would try to cut the edge which has more distance. Because suppose you have like 5 points in a space where points 1, 2, and 5 are together, but like 4 and 3 are also together, but a bit away from point 1, 2, and 5. So you'll try to cluster in such a way that 1 to 5 points are together and 3, 4 points are together. So what you can see is like this weight is nothing but a measure of similarity. It's like a arbitrary value which gives a metric of similarity. So what would I want is like you make a spanning tree and we cut the minimum, like the one with the minimum weight, because of which the maximum weight ones are retained. And this maximum ones are retained because you want the points to be close enough in one cluster and close enough in the other cluster. So like you cut this one to get two different clusters, and you can cut this one again to get like three different clusters because first this was like the least weight, and when you remove this one, you have 0.7, 0.8, and 0.5, and you remove this 0.5 because it has the least weight, and now you get 3, 4 as one cluster, 2, 1, 5 as one cluster. You get three different clusters. So this is how you proceed on like finding clusters using maximum spanning tree. So as I wrote it here itself, like what you want is like you want the clusters with more similarity or less distance are grouped together. And here you can also cut 0.5 this edge or this edge, but this is decided heuristically, like there's no solid formula of which one you have to cut. But looking at the graph, you can easily say that if you cut this one, you will get like one cluster as like 1 point and 4 points belonging to one cluster, which you won't want in a particular clustering algorithm. So you want like two clusters to be of necessarily the same size, so you get one cluster of 2 points and the other cluster of 3 points. So this is like a maximum spanning tree. And suppose like this is for the similarity matrix. If you had a distance matrix, then for a distance matrix, we'll make a minimum spanning tree such that you have the values between them. And then you'll cut off the maximum, like the edges with the most weight. Because you want the most weight in the distance matrix, like represents the max, like the distance is more. So you want to cut off the edges which have more distance, and you want to keep the clusters within which the distance is less. So that's why you can either like if you're given the similarity matrix, you can go with the maximum spanning tree and remove the ones with the minimum weight. And for the distance matrix, you can just go with a minimum spanning tree and then remove the edges with the most weight. So this is how you form clusters like using this maximum and minimum spanning tree. So now coming back to threshold graphs, like how do we proceed with threshold graphs? So first of all, like you have 5 points here, like you have like 5 points. We start off with each point to be a separate cluster of its own. And now like we just say it like you connect all the nodes in the graph in such a way that the similarity is greater than or equal to one. So if you have of these 5 points together and you try to connect those with like the similarity which is greater than one, all of them would be left alone. So none of them would be connected. And then you'll treat all the connected components, which are like zero in this case, as a cluster. So you'll have five different clusters in this. And now you start decreasing the threshold. What we want is like you have five clusters in the start, and now you decrease the threshold. So now if you decrease the threshold to say weight should be greater than 0.8, this edge gets included. So now you say all the connected components will be taken as a cluster. So now in this is a connected component because obviously it's not connected to anything. It's like self. All of these are taken as one like clusters one, two, three, and these two are connected. So you take it as one cluster. So you get four clusters in this. So like what the method between threshold graphs is like you connect and now you lower the threshold one after the other such that all of them are connected. So now you just continue the process and like decrease the threshold. And now suppose you say the threshold is 0.7. So this one gets connected. And now these three are connected. So these three are like one connected component. So this is like one cluster and this is another one and this is another one. So you get three clusters. And now if you put 0.6, this get connected. So like it does not connect, like 3 and 4 are still separated. It's not connected to this body. So it's still 3. So now you lower the cluster again, like lower the threshold to 0.5. And now 0.5 by this and this gets added to it. So all of them become a single cluster. So the threshold graph is nothing but you just decrease the thresholds and until you get a single cluster. So yeah, now we can also plot the dendrogram for this. And like you have the points on the x-axis like 1, 2, 5, 4, and 3. And you have the different threshold values on the y-axis. And now, so you can see at 0 point at 1, all of them were different. And at 0 0.9, same, all of them were different clusters. At 0 0.8, 1 and 2 were merged together, but these three were different. At 0 0.7, these two were merged. So 1, 2, and 5 were in a single cluster, and then 4 and 3 were different. So as you go on, you can like check the values and like see from the graph like at what value of threshold how many like points were together in a particular cluster and how many were like not there. So like this is how you plot a threshold graph. So now you have to like now we can cut the graph at any desired point. Say suppose I have to cut it at 0 0.6. I'll cut it at 0 0.6. I'll get this as one cluster, zero point 0.4, and this point number 3 as one cluster, and 1 to 5 as a separate cluster. So if I cut at 0 0.6 threshold, I'll get 1 to 5 as one cluster, 4, 3, and so I get three clusters at 0 0.6. So now, so do you see a similarity in this? So like if you like measure, like look at it close enough, so like single linkage is like forming clusters by connecting points which are like a minimum, like you calculate the minimum distance between the two closest point. And like if you imagine like drawing an edge between every pair of points within like a threshold and like you use the connected points and like you just like cut them. It's like more or less similar to connected components. So what I can say is like in this, what we do is like we just yeah. So we what do we do is like we cut off the component which has the least like weight. And like you add these points one after the other. Like you lower the threshold and you are adding values like 0 0.8 with this was added, 0 0.7 this got added. So what does it means? Like you lower down the similarity and then the values are getting added. So like this is nothing but you like you're just connecting two points which are like closer together, right? As you move on every step, you just connect two points which are like closer. So you can see like at this point, suppose like 2, 3, and 4 are like 3 and 4 are different. We get like this and this are connected, right? This gets connected at 0 0.5. So what do we mean at 0 0.5? This point could have been connected to this, or this point could have been connected to this. But at 0 0.5 similarity, this point gets connected. So in that particular case, as you lower down the similarity, you go down the similarity, you just increase the distance. So you connect the like the points which are like closer first. Like you decrease the similarity and you start connecting points, right? So decreasing the similarity would increase the distance. So what you are necessarily doing is like you're like connecting the points which are like close enough first, and then you move on. So like you're combining clusters based on the closest distance between them. So like this is similar to the single linkage. So yeah. So this is some like similar to single linkage because every point you're connecting the clusters based on the closest distance between the 2 points or like the highest similarity. So this is like for that. And now this was one method of using connected components. There's one more method of using maximal cliques. So before moving on to this, I would like to ask if anyone has doubt in this, they can ask me right now.
One doubt, is there a particular way you can get the similarity matrix given the distance matrix, or is the similarity matrix to be given if you want to form a maximal tree?
Yeah, so basically similarity matrix is like it's a measure of like any quantity which is similar. So based if you want to take like similarity matrix as a terms of distance, say suppose you want to define similarity measure as a like reverse of a distance. You say that 2 points are similar if they are like close enough. So that's how that's one way of defining similarity. There are other ways according to you you can define similarity. So like say suppose like other features of the data like I don't know how to put
So
forward,
it's not
but
rigid.
yeah.
So
What?
it's not rigid, right? Then
Yeah, it's
you
not
can choose
rigid.
anything
Yeah, you
that
can.
is
Yeah,
inversely related to distance as a similarity.
yeah, you can choose any of them. Yeah,
Oh, okay.
yeah, yeah. So now there's one more method of using maximal cliques. So first of all, let me define what is a clique. So clique is nothing but a subset of a graph in such a way that all the vertices in that particular subset are connected by an edge. So suppose if I have these 2 points as a subset, all these 2 points are connected together. So it is a clique. But suppose if I have 3 points connected together, and in this case, these two are not connected. So in this subset of 3 points, all the points are not together connected. So this is not a clique. So I think it's easier to like it's not so hard to understand what a clique is. In that particular subset, all of the vertices should be connected to each other. So all of the steps using maximal cliques are same, except for the fact we use cliques instead of like connected components to determine the clusters. So suppose we start off with the same fact that we have all the points as different, and now at 0 point, we lower the threshold again to 0.8, where you get like 1, 2 as like these two get connected, and it's a clique because within this 2 points, both of them are connected. So you get 4 clusters, and now you connect this one. But the thing to look here is like in this like 3 points ka subset, all of them are not connected. So in that particular case, this three cannot be like a clique of its own. So either 1, 2 can be a clique or 1, 5 can be a clique. So when we move forward with the concept of maximal cliques, we do not disturb the cliques which are formed in the previous step. So 1, 2 is an already existing clique, and like therefore 1, 5 won't be counted because it's nothing but overlapping. So again, we have like the same 4 clusters, this, and this, like the same, nothing changes at 0.7. So now, yeah, it's the same thing. You just like decrease the threshold at every step. And now when you decrease it to 0.6, these three gets connected. And now you can see that these three ka subset is like a clique because all of them are connected together. So like this is a subset, like 1 to 5, it's a clique of its own. So this becomes a cluster itself, and you get 3 and 4 as another clusters. So you get 3 clusters. And now at 0.5, even this and this gets connected. So now at this point, you get 2 clusters, 1, 2, and 5, and 3 and 4. Because 3 and 4 ka clique is considered because two subsets may all of them are connected, all of the connected. But if you take all of the points like 3, 5, 1, 3, and like 2, 3 are not connected. So in that case, 2, 4 is not a clique with any of that, and it does not overlap with the existing ones. So 3, 4 is like one more addition in this step. So you get this one as one clique and this one as one clique. So 1, 2, and 5 is like one cluster, and 3, 4 is like a one cluster. So you get 2 clusters. And at 0.2, all of these points are connected together, and all of these are connected together. So all of the 5 points are like connected to each other. So it becomes a single clique, and it's like a single cluster of its own. So it's nothing but moving forward with the concept of cliques rather than using the connected components. So like, what's the difference between both of them? So like, say if I have to cut the graph at 0.6, I want, so there's one way of looking at the similarity as well. I'll like to like put forward this. Suppose if I say that we want to cut the tree such that the similarity is at least 0.6 between any two nodes or like any 2 points. So you want like if you write this in terms of distance, you would want like say suppose you say I want a distance between two times to be like at least k. So you would at max k, so you would say the similarity should be at least something like q or p. So like you define, if you say something that the similarity is at least 0.6, so you'll try to cut the graph at 0.6 in such a way that you'll get the clusters. So basically it's like how you define the threshold. So like suppose if I'm like told to cut the graph at 0.6, like that's the threshold to cut the graph. In these two different methods, we can end up with two different uh, divisions of clusters, like two different cases. So suppose in 0.6, this was the graph for like connected components, and this was for the maximal cliques. So you cut it just below 0.6, like 0.60001, something like that. And in this case, you get 1, 2, and 5 as one cluster, 4 as one cluster, and 3 as one cluster. But in this case, using maximal cliques, when you cut it just below 0.6, like at least 6, so in that case, you get these 2 points like 1 and 2 as one cluster, 5 as different, 3 as different, and 4 as different. So in this case, you get different clusters. So we have already seen that connected components are more or less similar to using single linkage. So drawing an analogy in this particular case, we can also see that maximal cliques are nothing but using complete linkage. This is because you define a clique in such a way that this is defined a clique when you have all the points connected to it. And as you lower the threshold, the ones with the higher similarity gets grouped together first, like with the lowest distance get first, and until the like the one with the least similarity or like the maximum distance is connected to it, it is not considered as a cluster. So this is nothing but you're using the concept of like complete linkage until the like if the farthest distance points within that particular subset or within that cluster are connected, it is not considered as a cluster. So like you just basically for joining two different clusters, you use the farthest point ka distance. So this is nothing but same in the maximal cliques. You wait until you get the minimum similarity to connect all the 3 points. So in that particular case, we can see that connected components is similar to like using single link clustering, and maximal cliques is like similar to using complete link clustering. So as I said, in this case, you'll get 3 clusters, and in this case, you'll get like 4 clusters. So this is more or less analogical to that. So now, what's the advantage of using threshold graphs? So one of the best advantages of using like threshold graphs is like you can like use arbitrary numbers as your weights. So suppose I had like I connected these three together, right? Suppose if these were on a like on an actual graph, like these were in the graph, like where you have the data points. These 3 points, if I have like weights as 0.8, 0.9, and 0.12, like you have to find like if there are distances between it, you have to find so like you have to follow certain rules, like the sum of two sides should be greater than third side, as in the triangle inequality and all. But when you use the concept of threshold graphs, the weights can be any arbitrary number. Like it should be just related to the similarity measure, how you define it, and you don't have to follow any particular metric. So this is like a very good advantage for it. So you need not figure out how triangle inequality is formed or how geometry works in that particular case. You can take any arbitrary values as the weights. So this is the advantage of using threshold graphs. Now, if anyone has doubts till now, they can ask, or I can move forward to the cure algorithm. So yeah, I'll take it as no doubts then. So moving on to the cure algorithm. So this is also one of the more like one of the methods for using clustering. So this is like clustering using representatives. So we've already seen that in k-means clustering or hierarchical clustering, we use something known as the centroid. We like use the centroid to determine the cluster, and we take it as like a representative for that particular cluster. So what you do in like the cure algorithm is like you use representative points, which like are the representative of that particular cluster, and use them to use the clustering methods. So first of all, like in the case of like k-means clustering, you don't go around getting like banana shaped or other types of shapes of clusters. Like you usually get a circular or an oval type of a cluster. So what like most of the clustering algorithms fail in like non-spherical like clusters, they can't like they vary in size or density, and they containing outlines. These are like these are like the criteria where most of the clustering algorithms fail. So like Cure solves it by like combining representative points for a particular cluster and like makes it robust and scalable. So how does this Cure algorithm work? So first of all, you have like say suppose you have this as a whole data set. You divide it into like five or say five samples. You like divide the whole data set into five samples, and now you draw random samples from the data set, which is like one of them, and you run some sort of clustering beforehand itself, and you get few clusters in the graph. Like say suppose this was like one of the sample, you already got three clusters in this. So now what you do is like you choose some representative point for those particular cluster, and you like use and then you shrink them towards the cluster centered by a fixed factor. This is because like suppose I'll tell how the representative points are chosen, but this is like a cluster which is already there. You suppose we choose these 4 points as like the representative point for this particular cluster, and now you like push this towards the centroid by 20% of the distance. This is because like if there was a point which is like an outlier which was like taken as a representative point, pushing it towards the center would like benefit us, because like it would help in like the clustering thing. It won't be necessarily an outlier. So this is how you do it. Like you just choose the representative points, you shrink them towards by a factor of like alpha, like which is a hyperparameter, say 20%. And now you use this shrunk representative points to make new clusters. Like based on the representative points, instead of using like like in k-means, we use the new centroid to like assign the data points to the particular cluster. In this case, we use the representative points to assign the data points to that particular cluster. So like you just in that particular case, we just went on with assigning data points to a particular cluster, recalculating centroid. In this case, we just like assign and then recalculate new representative points and move on in the same way. So in this case, the important thing is how are the representative points chosen? So first of all, for each cluster, like you have like say suppose we say that there are k different clusters in the particular sample. Here case 3, like you can easily see that, and we select like say m equal to 4 representative points for this. So first of all, you have the center, and you choose the farthest point from the center as one of the representative point, and then you choose the other point which is like farthest from the first representative point. And now you choose a third, which is like the far which for which the sum of the distance is like maximum for from both of them. So you calculate that, and similarly you calculate the fourth one. So using the farthest distance thing, we calculate all of the representative points for a particular cluster. And now you just shrink them towards by a factor of like say alpha 20%. And now you got the representative points for a particular cluster. And now we can move like, and now just like k-means, you can go around with assigning the, like say, suppose you forget these like clusters, because in k-means also we do the same, and you assign a point, like suppose there was a cluster here and there was a representative point here. So which one is closer? You, based on this, you assign this point to that particular cluster. So this is how it works. And now this is what you do in a particular sample. And now what do you do with in the entire data set? So what you do is like, suppose we had 5 samples of like the whole thing, we run cure on each of them. And in each of the samples, you get k clusters, and each of the cluster has like say m representative points. So for each of the cluster, you'll get mk representative points. So each of the sample, you'll get mk representative points, right? So you have 5 samples in this case, so you'll get like 5 into m into k representative points for the whole data set. So now what we do is like, you have 5k representative points, and now you treat this as normal points. You use any other clustering method, or like say cure on this total 5 mk points again, and then you reduce these into like k final clusters. So like there were 5 mk points, and you make 5 k clusters again with like m representative points in each of them. So what you get is like, you a final, like after getting these 5 mk points, you do this thing and you get k clusters for the entire sample, like entire data set. And for each cluster, you have m representative points. And those m representative points are taken as the summary model for the entire data set. Now you have the final m representative points. And now you, for each data point, you calculate which representative point is the closest, and you like just assign it to that particular point. So this is how it works. So this is the more or less the, yeah, the cure algorithm. So does anyone have doubts with this? So yeah, I'll move forward with it. So yeah, the next thing you have is density-based clustering. So the clusters are defined based on the density of data points and not on the distance. So what were we doing till now is like, you define the clusters based on the distance, and now we are using the concept of density. So we need an algorithm, or like a clustering algorithm, which captures the notion of density, such that we cluster the data points based on the density. So now what you do is like, you in this, the clusters are defined as like the areas of high density and lower density. Like you separate the areas which have higher point density with the areas of lower density. So suppose this was like here the higher density, this is like a higher dense region, and this is also dense region, which is like separated by a lower region which has no, like, or like say 1 or 2 points in it. So one of the like algorithm for this is dbSCAN. So dbSCAN stands for density based spatial clustering of applications with noise. In that, what you do is like 2 points belong to the same cluster if you can move from one point to another through dense regions. Like in this case, if like say suppose this was a data set given to us, if you use k-means, you can like get 2 different centroids like this and 2 different clusters like this. But if you use dbSCAN, this whole would be a one data, like one cluster, because you can move from one point to another point through a dense region. So like this is like, so this is the difference between k-means and dbSCAN. And this method, like this algorithm, also helps us to like capture like different types or different shapes of clusters, and not just circular in case of k-means. So before moving on to how does this work, we need to understand what are like the few parameters. So first of them is like epsilon, which is like the radius of the neighborhood around a point. So suppose you take a point, you draw a circle of radius epsilon, and like this is like how far you want to search for neighbors. So this is like a centroid for that, like so a certain point, and you take an epsilon, and all of the points you check how many points are there. So like this defines the neighborhood, and this is the radius. So this is epsilon, and another thing is like min points. So min points is like, you define the minimum number of points that are required inside the particular region to consider that particular region as dense. So suppose if I say that in this, like 4 should be the min points, so it searches for a region in like radius r equal to epsilon. And if there are 4 points, then this is like considered as a core point, and like that's like the region is considered to be dense. Like this epsilon ka radius is considered to be dense. So what do we do is like, the minimum points helps us to decide if a point is a core point or not. So we like, I'll try to like describe you what are the different types of points in this. So first of all, there's a core point. So there's a point for which at a distance of epsilon, including itself, if there are the minimum number of points, there are at least minimum number of min points, like what we defined earlier in that particular region, then it's like a core point. And the other point is like a border point, which is like it's there in the region of a particular core point, but it's not a core point of its own. Like if you like put a radius of epsilon and search out for like a different like how many points are there in that particular radius, it would be less than the minimum points. So it's not a core point of its own, but it's like it's in a it's like it's within the range of a core point. So it's defined as a border point. And a noise point is like which is neither of both of them. Like it's neither this nor that. So now you have to define like let's move forward to density reachable and density connectedness. So like we need to define like a point Q is directly like we have to define these two terms. Something there's something known as density reachable and density connected. So a point Q is like said to be density reachable from point P if you like it's within the epsilon radius of the point P, and it's like the P is a core point. So suppose if P like this is a point P which is a core point and this is a point Q, and this is density reachable because this is like the point P is a core point and it's in the region of the epsilon. So that is told to be a density reachable point. And like you can also say that a point Q is density reachable from P if there exists a chain of points like P to X1 to X2 Q such that it is like directly density reachable. You can also define it as like a Q, like say suppose there was a point Q here and a point P is here. So you can move from P to Q using different points like P to X1 to X2 to X3 such that you go to Q. So Q is also density reachable for P. So this is how you define density reachable. And now how do you define if two points are density connected? So two points are density connected if there is a common point O from which both are density reachable. So say suppose if this was point P, this is point Q, and there's a point O. So from O, both of these points are like density reachable. So these are density connected with respect to point O. So this is how you define. So now what are the steps for like the DB scan? So what you do is like it's very simple. You start off with a core point, like a core point, and you run a scan, and then you like find how many core points are there. Like you just if you've already visited a point, you just skip it. And if like there are other points, you just move to one core point to another core point, and you find its neighborhood and then go to another like core point. So it's like you start off from a core point, add all the neighbors within epsilon, and you recursively expand to the neighbors of neighbors. And you keep growing until you capture all the points and no more points are left. So just if you go through this, so like if I read out this, so like you just if there's a point you have already visited, you skip it, and then otherwise you mark the point as visited. Find the epsilon neighborhood of those particular points, and in that particular point, like you just check if it's the min point is like it's greater than min point or less than min point. Like basically you check if that particular point is a core point or not. If it is a core point, you just start off from there again and you recursively expand. And if it's not a min point, you point like if it's less than the min point, you just mark it off as noise and you go back to the another core point which is left. So this is how you go. You just move from one core point to another and just capture all of it. So now I'll move on to the code implementation for DB scan. So yeah. So what do we do is like yeah, we just import dbscan from sklearn, and like this is nothing but an array. Like you just define a set of points like 6 points 1 2 3 4 5 and 6, which is like you can easily see this in one cluster, another cluster, and another cluster. And like you just scatter plot all of them, and now you just define what is the epsilon and what is the number of minimum points. This is like the min points. So if I said it's 2 and 10, and now you just run and like find like how many points are there, so it will like assign different values to it. So for that, all of them get clustered in like a different way. And like this is how you do it. And suppose like one of the major facts, as I said in DB scan, is like you can cluster in such a way that all of the points are not in like a particular like a circular shape. Like suppose like this all can be clustered together using like DB scan. You can cluster these points together and these points together, which is never possible using k-means. So what is the thing is like you just for this data set, I used make circles to like make two circles of points. And now like I define the epsilon as 0.1 and the minimum number of samples as 5. And now it goes from one point to another point using core points within the particular epsilon of 0.1. And because of that, it is able to navigate throughout this whole distance using the density region. And then for this, it goes on for a density region of its own, and you can cluster these two data sets differently. And suppose if I, instead of 0.1, I put it as 100. So in that particular case, you get all of the points to be in the same cluster, because for this the neighborhood would exceed till somewhat here. So in that case, you can easily move from this point to this point, because this is also a core point, this is also a core point. So in that case, all of the, instead of moving from just these points, you can move from here to here to here to here. So all of them gets clustered in the same way. So it is very important to determine and like decide what value of like thing you have to put for epsilon in such a way that this gets clustered in a better way. So this is how you like use dbScan. So I think, yeah, this is the end of this part, and now I think Lokesh can take over for the other part of the clustering thing. Wait, does
Yeah,
anyone have
sure.
doubts? So yeah, I think no doubts, then Lokesh, you can move on.
Yeah. Is my screen visible? Yeah, is my screen visible?
Yeah, it's visible.
So I will be continuing with Gaussian mixture models and the expectation maximization algorithm. So in the previous clustering techniques, we observed that after convergence, each point belongs to a particular cluster. However, there can be certain instances where a single data point can belong to multiple clusters with certain probabilities. Essentially, for example, if you have two clusters, then there could be possibilities where a point is 70% part of a cluster and a 30% part of another cluster. So GMMs give us the freedom for that. GMMs are essentially a probabilistic model for clustering data where each cluster is represented as a Gaussian distribution. Since I've introduced this term Gaussian distribution, let us understand what exactly it represents. Yeah. So a Gaussian distribution is essentially a statistical model that describes you how the data is spread out based on the average and how much it varies. So this is the Gaussian distribution in three-dimensional space. If you observe it from the top, you will get counter plots, which we will be using for as our clusters in two-dimensional representation. So in simple terms, if I explain, then Gaussian mixture models involves two steps. Step one is that you color the points according to the Gaussians. So as I said, it is a probabilistic way of assigning points. So you essentially define two Gaussians, and based on the distance of points from the center, you assign that how much it belongs to a particular Gaussian. For example, this yellow point is closest to the center of this particular Gaussian and is very far from this Gaussian, so it is completely assigned a yellow color. This is equidistant from the center in some terms, so it is colored as 50% yellow and 50% blue, and same goes for this point. So now it is important to understand that how we assign these probabilities. So consider that we are taking a one-dimensional data for simplification, and the one-dimensional data is essentially number from 1 to 10. So what you have to do is, if you project this curve onto the xy plane, you will obtain a bell-shaped graph. So I will be using that bell-shaped graph, and the data set which I will be using is a one-dimensional data which contains 1 to 10 numbers. So the x-axis represents the actual data points, and the height of the curve at any point x will give you the likelihood of x under that Gaussian. So if you take the x and input it into this function, then you will get the likelihood that this point belongs to this particular Gaussian. Similarly, you will calculate it for the blue Gaussian, and you will essentially get the soft assignment for a particular data point. Step two is the opposite of the first step. So in step two, we fit a Gaussian. So given some points, how do we exactly find a Gaussian? It is very simple. You have the x coordinates and the y coordinates of the data points. So for easier visualization, I'm considering a two-dimensional data, but there could be hundreds of features, and Gaussian mixture models work with those features as well. So consider that we have this particular data set. The mean is defined as the average of the x coordinates and the average of the y coordinates, or if you consider these as the weights, so it is essentially the center of mass of all these points. You also define a covariance matrix. The reason why we define a covariance matrix is because it captures the relationship between x and y axis. and also it gives you the direction in which the data is spread. So we define a covariance matrix. This equation gives you a generalized equation for a Gaussian distribution, and the equation below this is essentially giving you Gaussian distribution for a two-dimensional space. So these bell curves follow this particular equation. So if you have the values of x, you have the mean and you have the variance, you can obtain the Gaussian distribution. Okay. So before understanding the working of this model, it is also important to understand that even if we have the percentages of points, we can fit a Gaussian really well. Because if this particular point is, let's say, initially it was 2 comma 4, and we only take it as a 50%, then it becomes 1 comma 2. So there is no change in the calculation of weights. You can imply the concepts of center of mass, and you can understand that it will shift towards the part where more weights are there. So we can also define this for percentages of points. So in a nutshell, the GMM algorithm is following these steps. So you start with some random Gaussians. Random Gaussians means you initialize the means and the covariances, and you run a while loop until the model is not converging. So first step is you color the points according to the Gaussians, and the second step is you recalculate those Gaussians according to the colors. Okay, so this is very important to understand the GMM algorithm because it involves a lot of mathematics in it. So if you understand this, then it will be really easier to follow the maths part of it. So consider that this was a data set and we randomly initialize the means and the covariances of the two Gaussians. As I said, based on the distance of points from the Gaussian curve, we assign them the colors. So essentially, these 2 points are closer to the yellow Gaussian, so these are assigned the yellow colors. These three are closer to blue, so they are assigned blue colors. And similarly, since this point is equidistant from these two Gaussians, it is assigned 50% to Gaussian A and 50% to this particular Gaussian. So now what you do is you color the points. Now you have to forget these two Gaussians. And based on this new coloration, you have to calculate the new Gaussians. So what you can observe is while calculating this yellow Gaussian, you will completely ignore the blue proportions. Okay, so essentially when you completely ignore the blue proportions, you fall in this case. And once you fall in this case, you can easily calculate the center of mass, that is the mean and the covariance as well. So you independently calculate the Gaussian for the yellow distribution or for the yellow proportions and independently for blue as well. Then once you calculate these Gaussians, you have to color the points according to the new Gaussians which are formed because the location of the Gaussians have changed. So the probability assignment of the point will also change. So you color these points, then you iteratively run this algorithm until there is no shift in the Gaussians, or you can say there is no convenient change in the mean and the covariance. Okay. So if there is any doubt in the algorithm before, then please ask. Okay, so I'll take it as a no. So let's understand the maths behind the Gaussian mixture models. So as I said, the goal is to figure out the best possible parameters, mu, the sigma, that is the covariance, and this particular term pi, which I will discuss later on, why we need to define this. So it will be easier to explain you the mathematics if we consider a real world problem statement. So one more insight that the human heights also follow the Gaussian distribution and stock returns also follow the Gaussian distribution. So for example, we have a data set of fruits with two measurable features. Let's say we have the diameter and the weight. And the fruits are of two types, but the labels are unknown. Obviously, since it is a unsupervised way of clustering, we have unknown labels. So what we do is we aim to cluster the data into two groups using Gaussian mixture models. So we will initially define two Gaussians. So this is the Gaussian A, which I have defined, and this is the Gaussian B, which I have defined. This is nothing but the fx, which I introduced previously. So this tells you that how likely x was generated by the TF Gaussian. Okay. So now if I have the diameter and weight of an observation x, I need to compute the probability of x being generated from a Gaussian A or Gaussian B. So this particular equation gives you the probability of x being generated from a particular Gaussian distribution. So this term pi is nothing but a prior we define in uh, Gaussian mixture models because it is helping us essentially to perform soft clustering, and it also represents the real world data which is imbalanced. Also, these priors are nothing but if there are n particular Gaussians, then what is the probability of selecting the kth Gaussian? So these priors are defined to make the data or to replicate the data set which is present in the real world. Also, these priors are learnable. That is, we will update these using the expectation maximization algorithm. Okay, so now this particular thing which we defined is for a single data point, but we need to maximize the probability for all the endpoints in the data set because that's the main uh, that's the thing which we want to reach, that is the convergence. So how do we reach the convergence is by maximizing this particular probability. So it is essentially you can apply the formula for independent points that if this contains n points, then we can split it into the multiplications. So this is the equation which you will get. But this particular equation, if we try to maximize, then it is intractable or very difficult to compute. So what we do is we prefer the taking the log likelihood. There are several reasons for which we use the log likelihood. First reason is that essentially these are probabilities. And if you have a lot of points in your data set, if you have thousands, 10,000s, or even 1 lakh points, then this value will tend to zero, which we don't want, and it will be difficult for computation. Secondly, it is difficult to optimize. Why it is difficult to optimize? Because uh, taking the derivative of product is always difficult than taking the derivative of sum. So this is the another reason which we use this log likelihood. Also, we use log likelihood because we are essentially scaling this p of x. It is not harming our maximum or something like that because log is also an increasing function. So as I said that we have to maximize this particular quantity. Now, how do we maximize this quantity? We use the model parameters, that is the mu k, sigma k, and the pi k. We take derivatives with respect to mu k, sigma k, and pi k and equate it to zero. By equating it to zero, we find the best possible values of mu k, sigma k, and pi k. So to compute those derivatives, we have to define certain quantities. So we define a variable or a random discrete variable called z. So z is essentially a cluster assignment. So it is assigned as 1 if xn is in class K, and it is assigned 0 if it is not. You can also consider z as a one-hot encoded vector in case of if we have two Gaussian distributions, or else it can also be a continuous distribution if we are using a probabilistic model. So for each data point, since we don't know that which particular Gaussian generated our data point, so we calculate the expectation of that particular Gaussian generating a data point. So this is what we define in the expectation step of our algorithm. That is the responsibility of component K for xn. So it essentially means that the probability that our observation belongs to a particular class K. Since I said we don't know that which Gaussian generated a data point. So we instead focus on computation of the responsibilities. Okay, so since this is a conditional probability, we can apply Bayes theorem, and you can separate these terms, or you can simplify these terms into these quantities. Probability of zk is essentially choosing a particular kth cluster from all the clusters. So it is the prior which we introduced earlier, and this particular term is nothing but the if you are given the model parameters, what is the probability of xn coming from that particular Gaussian. So it is nothing but the likelihood of xn under the Gaussian, and probability of xn gives you the total probability. Now one more issue here is that you have to do this for all particular z's. Okay, so if you have a lot of z in your model, if you have 3 4 clusters, or even if you go deep, if you have variational autoencoders, even they have a deep network, so they essentially use a lot of clusters. So it is computationally intractable to compute this particular quantity, because if z is a continuous variable, you have to perform integration over these steps, and you know that z is a vector, and integrating over so many dimensions is not computationally efficient, and it is very difficult to compute. So what we do is we later introduce a tractable distribution from which the z might have come, and we try to make that tractable distribution as close to this particular quantity, so the algorithm reaches the convergence. So essentially all these things we are doing, so we find the best possible solution. But since Z is a latent variable, we don't have any idea from where Z came. We use a simpler distribution and compute Z from there. So we will dive into EM algorithm and understand how it is happening. So as I said, we define these quantities to maximize the log likelihood. That is the ultimate aim which we achieve, which we want to achieve. So what I said before also, that we have to take derivative with respect to mu k, sigma k, and pi k, equate it to zero to get the optimum value of all these parameters, so that model reaches convergence. But this is also not efficient to calculate, which I will discuss in the expectation maximization step. So right. So these particular formulas which have been derived are not from this quantity, because taking derivative of this is also not easy, because you can see essentially it is a log of sum. So when you will like differentiate with respect to, let's say, mu k, so you need to know the values of sigma k and pi k, and you know that you are updating these values after every step. And after every step, since you are updating these values, these distributions will keep on changing. So since these distributions will keep on changing, you need something such that if you take derivative with respect to mu k, only the mu k term appears in it instead of all these sigma k's and pi k's. So like, since you will be taking derivative with respect to mu k, all those quantities will tend to zero or become zero. So you can easily compute the maxima. So, but this particular function will not help us to calculate that maximum value. So instead we use expected log likelihood, so that we can essentially get the optimum solution. So these formulas are derived by taking the derivative of that expected log likelihood, which I will be sharing further, which I will be explaining further. Okay. So if anyone has any doubt before starting EM algorithm, please let me know. Okay. So I'll be continuing with the EM algorithm. So in EM algorithm, we have to initialize, that is start with the model parameters, as we did in this particular step as well, where we initialized certain Gaussian distributions. So it is essentially you are defining the mu's and the sigmas. So after you start with certain model parameters, you compute the log likelihood based on these parameters, and you repeat this for t iterations. You start from m is equal to 1 to t, and you define the expectation step and the maximization step. So what you do is you compute the responsibilities, that is the posterior distribution of latent variable z, that is probability of z given x and b. But as I said, that it is not tractable to compute because of the denominator which is appearing below, and z could be a high dimensional vector. So we want to avoid it, and we will try to take a different distribution which will help us reach this particular quantity. Okay, so here is some more explanation about z. So z is essentially a hidden variable which is telling which Gaussian generated each data point. So we don't observe that particular z. So EM algorithm estimates it as a probability in the each step. So it is telling you which Gaussian component the data point came from, but you don't know which Gaussian component actually generated that data point. So here is the example also. You can check it out. So in the third step, as I said, that calculating the or maximizing the log likelihood is not an easy task. So instead, we use expected complete data log likelihood. That is, we define the Q function. So this is the definition of Q function, and we will derive this Q function using the Jensen's inequality, which I will cover further. And in the M step, what you have to do is you have to maximize this particular expected log likelihood using the same derivative with respect to the model parameters, that is mu k, sigma k, and pi k. So instead of taking the derivative of log likelihood, you will be using this particular expression for calculating the best parameters. And then you have to repeat this algorithm and check for convergence once there is no change in the log likelihood. Okay. So I will be showing you how to derive the Q function using the Jensen's inequality. So this is the refresher on Jensen's inequality. You consider f as a convex function which is defined on interval I. You consider data points belonging to this interval, and these are the weights which are greater than 0. So we define these weights just for a better proof and better generalization of the model. So this is the Jensen's inequality, which states that f of weighted sum is always less than the summation of all lambda f of xi. So you can see if this is valid for the convex function. So the concave will have exactly opposite sign for the Jensen's inequality, and since log is a concave function, we will be using this particular expression for deriving q. Here is the Jensen's inequality for convex function. You can observe that this particular quantity that is on the left hand side is less than this particular quantity, which is essentially lying on a line, and it is following a sections formula. And these are the two data points which we have considered. Okay, so this Q function is also known as the evidence lower bound. So we will be deriving this evidence lower bound using the Jensen's inequality. So as I said that we don't know that we need to calculate the gamma, that is the responsibilities in the expectation step, but it is intractable to compute. So we will be using a tractable distribution, which could be Gaussian distribution or any sort of distribution, which gives us some initial model parameters, and using those parameters, we will be able to maximize this function and make it equal to the true responsibilities. So this is the log likelihood which we have taken, and we just this is like acting as a likelihood. Like we have the Gaussian distribution equation as f of x. Similarly, this is also similar to a Gaussian distribution only. So this is also representing a likelihood. So we take the multiplication and divide it by the likelihood, and consider this term to be the lambda I and this particular term to be xi. And once you apply this particular equation, you will observe that this gets splitted into this. So this is essentially playing the role of lambda I, and this particular quantity is playing the role of xi. So this is the actual or the expected log likelihood, which would be optimizing or maximizing to reach the true log likelihood. So you apply the basic properties of log, and you get this particular expression, and this is the derivation of the evidence lower bound. Now what we have to do this, we try to maximize this particular lower bound. So this was the expression which we obtained here. We would be taking this expression for computing the best particular model parameters. Instead of maximizing the log likelihood, we would be using this particular distribution. So how it is done? It is done in two steps. First, we split the numerator. So essentially, you apply the properties of conditional probability, and you take the denominator on RHS and multiply it with the LHS, and you obtain this particular expression. Now you consider this particular entity as A and this particular entity as B. You split these using the log properties, and you observe that this first term is the KL divergence. So now what is the significance of KL divergence, or better I would say it is the negative of KL divergence. So we need to understand KL divergence because it will help us to maximize this particular likelihood function. And this likelihood, if we get to maximize, then we would be able to reach the true log likelihood. Because since this is less than equal to, if we try to maximize this particular quantity, it will become equal to this log likelihood. So that is the thing which we'll be hunting for. So we would try to minimize this KL divergence. So what is this KL divergence? KL divergence is essentially measuring the difference between the two distributions. It tells us that how far our guess, that is how far our tractable distribution is from the true posterior, which we can't calculate. So we use scale divergence because we don't know this true posterior, as it is intractable to compute. So instead, what we do is we assume a simpler distribution, that is the tractable, and you can like give initialize certain model parameters to it, like mean, covariance, and the priors, and try to make this particular thing close to the true one. So this is what we would be using in the expectation step now onwards. Okay, so as I said, our goal is to now make the elbow, that is the evidence lower bound, closest to the actual log livelihood. So this can be done by making the KL divergence equal to 0, which is the tightest possible bound. So since this is the negative of KL divergence, if you want to maximize the function, this particular function, you have to make this 0 because KL divergence is always positive since it is essentially giving you a probabilistic representation. So this term is always positive, and when it is multiplied with negative, it will tend to decrease this particular function, which doesn't solve our problem. So we would be making the KL divergence as 0, and KL divergence is 0 if the tractable distribution which we have assumed becomes equal to the true posterior. Okay. So, but since we don't know the real model parameters, we would be doing this iteratively using the EM algorithm because I don't know what these model parameters are. I will initialize it, but since I have to update it step by step, I have to use the EM algorithm to iteratively update this particular function and try to make it close to the true posterior. So we want to maximize in summary, if I want to say it, we want to maximize the log likelihood, but it's really difficult. So we lower bound it using an approximate distribution psi, and the best lower bound is when these two become equal, but the model parameters are unknown to us. So what we do is we iterate, we guess the psi, and using the old model parameters, we update the model parameters and use that particular guess. Also, to give you insights on why maximizing this log likelihood is hard. So as I said that if you have the model parameters and you want to check the likelihood of X being generated from that particular model parameter, if Z is a discrete function or is a discrete variable, so you have to sum it, and if Z is continuous, you have to integrate it. But the problem is that if there are thousands of data points, there could be multiple assignments of data points for each cluster. So essentially, it is very difficult to keep a track of this particular probability. So and even in case of integration, you have to integrate over a high dimensional vector. So it is not tractable. So instead, what we do is we use this tractable distribution for which we know the model parameters and try to optimize it. So this is what I was trying to say. It is summing or integrating over all possible configurations of the variable z. The sum or the integral can be intractable due to a combinatorial explosion for discrete latent variables or unsolvable for integrals if it is continuous. So this complexity is preventing us directly from finding a closed form solution for the parameters by taking the derivatives of the log likelihood. So this interactability is what EM algorithm is addressing, and it addresses it iteratively by maximizing the lower bound on the true log likelihood. So let's see how the EM algorithm maximizes the expected log likelihood. So before diving into explanation of this curve, let me explain you what all these curves represent. So the red curve represents the true log likelihood, which we want to maximize and reach this particular point. And because that is the point where we will be getting the best model parameters. And this is the evidence lower bound, which we would be maximizing in this step because computing this particular quantity is very difficult for us. So we would be using, we will be taking the help of elbow to maximize the log likelihood. So these are the steps. We will, as I said, initialize certain parameters, that is the mean, covariance, and the priors. And since we can't compute the true log likelihood directly, so we would be maximizing a lower bound. That is, we would be trying to maximize this lower bound. So initially, we would be choosing uh, psi of z is equal to pz given x and theta old. So this is the implementation of KL divergence where these two become equal. So what we are doing is we are making the KL divergence 0. So you can observe that we get a tight bound at this particular point. So since we are getting that tight bound, we have reached the maximum log likelihood here. So, but the thing is we want to reach this particular point. So what we will do is we will try to maximize the lower bound with respect to theta, keeping this Q function fixed. So we are considering the M step here. In M step, we are updating the model parameters based on the Q which we have chosen, based on the psi, that is the distribution which we have chosen. So based on these new model parameters, we reach the maximum for the elbow, that is the expected lower bound. So here we reach the maxima for it. But as you can see that this at this particular point, the bound is not tight. Okay, so this, since it is not tight, we have not reached the convergence or the maximum log likelihood. So we will update Q based on these new model parameters. Sorry, we will update this psi on new model parameters. And once you update psi on these new model parameters, you will observe that you get this green distribution. And this green distribution is tight at this particular point, which means that we have achieved the closeness to the actual log likelihood. So since you can see that the log likelihood is increased once we update the model parameters, so it is helping us to reach the true convergence and in a much more efficient way. Also, it is much easier for taking the derivatives of this term because we have split it into the we have not taken the log of sum. We have split it into the summations of all the logs. So if you take a derivative, then you will be considering only one term at a time instead of the log px on the left-hand side of the Jensen's inequality. So also, since there is a problem here as well that we have to choose how many number of clusters or components we need in the model. So there are no certain methods or no certain fixed criterias. You can try various, like you can try Gaussians from 1 to 10 and see which gives you the best particular solution. But there are certain alkyc and Bayesian info criterias. So what essentially you do is you select the value of k such that this particular cost function is minimized. So this is again the cost function, and you add a penalty for this as you do in other machine learning models as well. So what alkyc info criteria does is it applies penalty linearly for high values of k, and Bayesian info criteria, if the number of data points in the model increase, it applies penalty logarithmically. So yeah, if you have any doubts, please let me know before moving into the code. Okay, so I will move into the code part. 1 second. So this is the code implementation of Gaussian mixture models. You import certain tools, that is the random you import certain libraries, you import random for the random selection of clusters, you import NumPy for numerical operations, you import multivariate normal for calculating probability density of points under the Gaussian, and Matplotlib for visualization. So what you do is you define a class GMM, and these are the constructors. So as I said that in Gaussian mixture models, you need to initialize the number of Gaussians you want, and the number of iteration also you need to run for EM algorithm. So these two quantities you define, and then you initialize this particular class on the dataset which you will be generating. So dataset I have generated below. It is a simple two-dimensional dataset for better understanding and visualization. And the rows of the dataset will give you the number of points, and the number of dimensions will be given by the columns. So our dataset contains 1,000 points and 2 dimensions. It is a two-dimensional data. Then you initialize the priors, that is the pi, and you initialize equal mixing coefficients or priors. Then you initialize the probability, you initialize the responsibilities or the weight matrix, which you initialize with zeros because you right now don't have idea of that. So you define the according, this is a 1,000 cross 2 matrix since our data set is of shape 1000 cross 2. Then you randomly choose k points as initial means and initial covariances. As I said that you have to start with certain guess for Gaussian distribution. So you will be choosing uh, random indices or using k data points initially and calculate their means, and similarly you will calculate their covariances. This is the training of GMM algorithm. So you initialize on this particular dataset or the generated dataset, and you define your expectation step and the maximization step. As I said, in the expectation step, you need to compute the responsibilities, and in the maximization step, based on these responsibilities, you have to update the model parameters. So in the expectation step, what you do is you use the function called predict underscore proba x. So what this particular function does is it gives you posterior probabilities for each data point belonging to each Gaussian component. That is the responsibility which we get. And based on these particular weights, you update pi. How this pi is updated, as I showed you in the slides as well. This is the equation which we are essentially doing. We maximize the expected log likelihood by taking its derivatives with respect to the model parameters. And once we equate it to zero, we would be getting these particular equations. So that's what I'm implementing here. So this is how we define the weights, and we update the pi based on these weights. And in the M step, we would be extracting the responsibilities of all the data points for cluster I. And based on these particular responsibilities, we would be updating the mu and the we would be updating the means and the covariances. Because once you calculate the responsibility, it is very easy to compute the means and the covariances. So you update the mu, you update the sigma. Then in the next step, as I said, that we use a predict proba function in computation of the responsibilities. This is an inbuilt function in scikit-learn library, but just for understanding purposes, I have included it here. So you understand that how essentially this function works. So this is nothing but you are applying Bayes theorem to compute this. But as I said that this is not tractable. So what this particular function does in the backend, it also tries to assume certain tractable distributions, and using those tractable distributions, it tries to maximize this posterior distribution, or you can say the responsibilities. So we essentially use uh, the psi function which I introduced earlier to compute the actual probabilities. And this is essentially the application of Bayes theorem. So this is the likelihood, and you multiply it with the pi, and the denominator is sum of all such likelihoods, and you return weights. So you iteratively run this algorithm for the number of max iter steps you have defined. So now I have defined the like I have created the model of GMM, where I initialized with 2 clusters, and the maximum iterations for which I would be running the EM algorithm is 100. So this is the code for generating the data. So we use the multivariate normal to create this data set and essentially visualize this particular data. I have not initialized any covariance, but you can try and initialize it. It doesn't create any difference. It will just change the direction in which the points are dispersed. And 42 is used for reproducibility. So you fit the GMM model on this data set, and you compute the responsibilities using the predict proba function, which I introduced earlier. And based on these particular probabilities, you will be assigning the colors as we did in the previous, as I did in the presentation. So this is the overview or the image of what the final distribution brings on the table. So you can see that this is a soft clustering method, and based on the probability of a particular data point being belonging to a cluster, it assigns a data point a 70% chance of being part of this particular Gaussian and 30% chance of this particular Gaussian. So essentially, most of the real world data is of Gaussian distribution. It follows Gaussian distribution. For example, the heights of humans follow Gaussian distribution. Even the stock returns follow Gaussian distribution. So there are various real-world data following the Gaussian distribution, and this model gives us a soft assignment or lets us know that yes, there is a chance that a particular data point might not be part of this cluster. So you look closely to that particular point and try to pay attention to it so it doesn't impact you in future. So yeah, this was the code implementation. If you have any doubts, please let. Yeah, then okay, thank you.
Okay. Any guys have doubt regarding the session? If there are no doubts, put thumbs up.